begin with the displacement current. Okay, we'll give some symbol ID for it. Okay, let's start with the capacitor. And now I think we are in far better position to answer most of the things. This is EMF, cell of EMF, say like a E naught, this one, or V naught you put it. The resistance are, they're having a capacitance C. Initially, there's no charge at T equal to 0. At T equals 0, so there's a condition what we have, capacitance. Now, I close the switch. What will happen? The capacitor gets charged. Okay, somehow I convinced you. I didn't explain actually. So we all know that. So as I close the circuit, as I close the switch, no. Okay, you can see air gap, no? Let's time being, let me put air gap. Is it possible for the current to flow through air? I'm asking this one best question. Is it possible for current to pass through this? Means capacitor or both are same? No? It's like an open circuit, no air gap. How come current will flow here? There's a discontinuity is there, no here? Discontinuity. Here continuity is there. Here there's a conductor present and the electrons will flow through this. But what I put here, there's a discontinuity. How come current will flow? I think some for capacitor to get fully charged, a current should flow. That's what we have shown. So there's a current. Okay, there's a conduction current. And we have started like this, no? How come current here? Current will not jump. So what actually goes on here? So there's a discontinuity is there. So this has to be explained clearly. So when I go and check it, no, here. So as this t is less than steady state, so it will attain some steady state after some long time, at any time t. I'll keep a compass needle here. It will start deflecting. And when I keep compass needle, no deflection. What is this? There's a compass needle. We'll take the symbol like this here. Will it show any deflection? No deflection. By the needle. You may, and now it start deflection. Now you may say that as a current flows here. Due to this varying current, there'll be magnetic field here high because of that, and as there's a varying current, so B equal to mu naught I by 2 pi r, go back to electromagnetism. So therefore B here is varying. Because of that, the needle gets deflected. I'm going to shield everything this. I will shield it. So how to shield this? By using non-magnetic material. I will shield this wire. I will shield this wire so that what all the current, what all the magnetic field produced by the wire should not exist till here, should not come into existence till here. So like that, I'm going to shield these wires. Or I'll make them shorter. That one I'll shield it. So let's assume that one. So these connecting wires are shielded or covered by non-magnetic material. Still, I'll see that a deflection in the magnetic needle. deflects. And finally, what happen, it will attain a steady state. So that will take it as Q infinity. Okay, what is that Q infinity? Q infinity or steady state charge CV naught. Okay, if I go and check now the needle, if again if I check the needle, no deflection. Compass needle it is, magnetic needle or compass needle, no deflection. From where this magnetic field is coming? So this was the primary question we have to ask it. We have to search for a source. Is there anybody who will produce such magnetic field? Okay, now let's go to Ampere's circuit law. Shall we go for Ampere's circuit law? I will start the loop like this. There's a loop. It's a loop, Amperean loop, or Amperean loop or Amperean curve. So then I'll pick up a point on it. No. Because of, I'm saying magnetic needle deflects means what should happen? There should be a current, no? Here, the magnetic field should be non-zero. So definitely here in the second diagram. So here also, there's the Amperean loop. So this is the Amperean loop. So what is the magnetic field at point P in the first diagram? BP is 0, no? I think I'll write it clearly. Why 0? Because there's no current carrying element. So in the first diagram, the magnetic field strength is 0. Why? Because Amperean loop will not enclose any current element. In our entire experiment, the connecting wires are shielded by non-magnetic materials. I think, is it okay? So let's not bother connecting wires. Leave it. It's of no discussion of that one. So why look at the first diagram. The first diagram, second diagram, third diagram. Okay, I am asking all of you to come to the first diagram. Why the magnetic field is 0? Because there's no current carrying element. There's no current carrying element enclosed by the Amperean loop. That's why what happened? The magnetic field is 0. Okay, just fine. Because I 0, the magnetic field is 0. Now let's come for this one. What is the magnetic field at point P? It's non-zero. Magnetic needle deflects means what happened? The magnetic field is non-zero. Now, where is the current carrying element? Any wire is there here? Any current carrying wire? Nothing. No, I'm not. We are not seeing. We are not seeing any current carrying wire here. Sir, what about this? I already told you. I am going to what like? Going to shield them. I'll cover them by non-magnetic material. Finish over. Connecting wires are shielded by non-magnetic material, so they don't produce any field. They don't produce any field nearby capacitor. There's a main thing. Okay, now second diagram, I'm clearly seeing that non-zero. Now, what is the conclusion I should make it? Where is the current carrying element? Now we'll ask ourselves question. Where is a current carrying element enclosed by the loop? Okay, agreed. Not one question, 2, 3, 4, 5 times we'll analyze. There's no current carrying wire, no? Then how come the field is produced? So definitely, and once again come for here now. Again the third part. Again, if I come and check it, steady state, the capacitor attains steady state. So charge across capacitor constant, the electric field is constant, and the magnetic field at point P is 0. Any reason for that? No current carrying element, because Ampere loop will not enclose any current. Okay, I think that we are very good in giving reason in 1 and 3rd, but what happened to us? We are totally failing to give any expression for the second circuit. Will I agree this? Okay, sir. Here, now, what is the here? This IC also, I'll call it as a conduction current. What is IC? It's the current that is flowing in wire due to conduction electrons. So shall I use word conduction or nothing but free electrons here? So what is IC? IC is a current flowing in wire due to conduction electrons. And what is that IC? Shall we say that charge at any instant of time in capacitor, let it be Q. So this, I'll write it as dq by dt. So why do that current? The charge across capacitor is increasing. So therefore IC equal to dq by dt. We know RC circuit, everything. So everything is fine except that why the magnetic field is non-zero. So we do have something. What is that? There's an electrostatic field will be present. We'll draw a line. See? What are this? There's an electrostatic field. Okay, look at this electrostatic field. Shall I? I think there's a discussion. We'll keep it here. No. What is the expression for charge? Q is equal to CV naught 1 minus e to power of minus t lambda. Similarly, what is the expression for electric field? Should be equal to Q by A epsilon naught. CV naught A epsilon naught. Okay, let's have that one. Look at the electric field. Is it a constant or variable? The electric field between the plates in second diagram, is it a constant or variable? It's in fact variable. Still our question, who will produce that magnetic field? We don't know. Okay, what is the only source available? The electrostatic field only. Okay, let's go back to the Faraday's law. How that induced electric field is produced by the varying magnetic field, no? The induced electric field will produce in Faraday's law. Induced electric field will produce the varying magnetic field. Similarly here, a varying electric field is going to produce this magnetic field. So why do this compost needle deflects? Because of that one. And if any magnetic field is produced, means there should be current element. So I'm going to introduce a new quantity called as a current density. Don't think that a current is flowing here. A varying electric field will produce a magnetic field. And because of that, the compass needle deflects here. If a magnetic field is present, means according to Ampere's circuit law, there should be current element. So therefore, we introduce a quantity called as a current density, but don't think that any wire is there. So a new way of think what you have encountered here. What is that? A varying electric field is in fact here produces magnetic field. So therefore, now can we apply our Ampere circuit law? So let's see that what Ampere circuit law says. B bar dot dl mu naught I net. So what is the biggest problem here? High net 0, but this is non-zero. So this has what happened? Violated an inconsistency in Ampere circuit law. Okay, some problem is there, no? Able to get this? I think I'll finish off this topic. It's over. Nothing big. Just only thing is, according to Ampere circuit law, the magnetic field produced at a point will be non-zero if there is any if that Amperian loop encloses a current here now. So what is the net current enclosed by Amperian loop? It is in fact 0. But still what happened? We are getting the magnetic field is in fact is equal to non-zero here. So this shows that there's some problem with the Ampere circuit law. So for that purpose what happened? I'm going to modify it. I'm going to modify it. So how that this one? So here what happened? The Maxwell he came into picture. He said like no problem. The Ampere circuit law will just modify it. And what he said like, in fact, here the magnetic field is produced by not due to this current carrying in a wire. In fact, a variable electric field will produce that magnetic field. Okay, that one. And to make the Ampere circuit law consistent to be applicable in all situations, so he introduced a quantity called like a current density here. No current carrying wire here. It's a air. It's a air gap. There's a air gap here. Pure air gap. I will write that also. Some of you are asking, sorry, what is present between the capacitor? Air gap. Okay, clear now this one. So for that purpose, he has introduced a quantity called as a displacement current here. Okay, all of you. So this is a very nice, you can say like a simplified approach, what we have. So let's proceed like this. So what is the displacement current? So we'll define like this. I'll magnify things. So the displacement current which is flowing there is equal to F naught into rate of change of electric flux. What is electric flux? How we define electric flux? E into A. Go back to Faraday's law or select Gauss law. E into A. So substituting this, the displacement current is equal to E. I'll take outside dE by dt. And we know what is the electrostatic field given by E equal to sigma by epsilon naught is equal to Q by A epsilon naught. Substituting that, the displacement current is equal to so what is equal to rate of flow of rate of charge on the capacitor plate. That is what I'm calling it as displacement current. Charge on a capacitor is varying and that will result displacement. This displacement current is what I'm going to introduce here in the Ampere circuit law. So now modified Ampere circuit law will come like this. So mu naught into conduction current plus displacement current. Now next question comes. Can we apply now can we give suitable reason why that magnetic field is? In fact, there is no current element, but because of displacement current, what happens? The magnetic field is non-zero. So between the plates of capacitor, there is a current density is there, or you can say displacement current, loosely speaking. Due to that displacement current, the magnetic field is non-zero, and there is no conduction current. So we have conduction current and displacement current. I think I should not show any displacement current like this. It's not justified, because there's nothing like a conduction current. The electric flux varies. The time varying electric flux will produce magnetic field. So to explain using Ampere's circuit law, we are introducing a concept called a displacement current, better called current density. No, between the plates of capacitor, what is IC? IC is zero. The displacement current in fact exists. Because of that, there's a magnetic field. Got the idea? Because of that, what happened? It'll be there. Okay, now let's see that one. Why there the magnetic field is zero? Because there is no conduction current, no displacement current. I think first diagram, shall I justify still more systematically? In the first diagram, why the field is zero? Because there's no conduction current, no displacement current. Then here, there's the electrostatic field is there. Don't think that no electric field. There's the electric field. I'll draw some 2-3 lines. E naught, I'll call it. So what we have electrostatic field, and it's a constant. And what is the conduction current? Zero. No longer capacitor gets charged. And what will happen to the displacement current? No, then that's why the field is zero. Why now magnetic field is non-zero here? Why the magnetic field is non-zero here? Because of the displacement current, not due to conduction current. So between the plates of capacitor, so this equation will end up like this. IC will be zero. You should write mu naught ID. So therefore, what is the expression we should write here? IC should be zero, non-zero. Between the plates of capacitor should be zero. At point P, IC should be zero. So therefore, now a suitable expression is in the third circuit, there is no conduction current. Charge is present and the electrostatic field is there. If I go and check it, magnetic field is zero. The reason for that, there's no conduction current, there's no displacement current. Okay, agreed? Got this? So here we thought there is no any current here, but in fact there is a current called a displacement current. That is what responsible for this magnetic field. Since E bar is varying, the magnetic field also is going to vary here. It's very simple. So what is the displacement? Constant or variable? It's a variable. That's why the magnetic field is variable. So who is producing that variable magnetic field? Due to varying displacement current. Why displacement varies? Because charge varies. Electric field varies. Why electric field varies? Because charge is varying. Because capacitor is getting charged. Okay, like this, the story is what we have built up here. Okay, agree. This so like this, what happened? The modified Ampere's circuit law. I think this is something at point P. So strictly, this is at point P or between the plates of capacitor. After this, how to calculate displacement current? Finally, what I got displacement current dq by dt. No, and what is the expression for conduction current? It is also dq by dt. So shall I say that both are same? So how much of conduction current that is existing in the wires? No, that much will be the displacement current. So how do you can see? Okay, look at the way I derived here. What I got displacement current dq by dt. What is q? Charge on a capacitor. Charge on a positive plate of capacitor. Similarly, what is a charging current across a capacitor? It is also dq by dt. So what is the displacement current? The current that is flowing through a conducting wire. That's all the conduction current, and that depends upon the rate of flow of charge or the the rate at which charge on a capacitor changes. Current flowing in a wire due to conduction electrons. Okay, got this. And what we got finally, displacement current. Now you ask questions, sir, like here. In here, conduction current is there and no displacement current. What about here? There's no conduction current, displacement current. I think I'll give one diagram so that students will get a clarity that what actually you are studying. Huh? Okay, let's take this one. Magnetic needle deflects. Okay, now let's write some very important information. So what is the conclusion? So shall we put here? So what is this? This is a like a conduction current, no displacement current here. Here, where the displacement current exists, where electric field varies. Where the electric field varies between the plates of capacitor. Finish all. Here, no displacement outside, no displacement current. Here also no displacement current. And what about conduction current? Here, the conduction current is not be there between the plates. Conduction current will be there in the wires here. In the wires, only conduction current flows and no displacement current. Now, what about here? So what is the comment we have to put it? At this particular point, what is the comment we should put it? No conduction current, only displacement current exists between the plates where electric field exists. I think this is the one thing which I had to put it in a very systematic way. Yeah? So don't think that displacement current is there everywhere. No. The displacement current exists only in the region between the plates of capacitor. What about here? No conduction current. I think I'll write it here. I don't know. I'll write it a note. No conduction current exists between the plates of capacitor. And in turn, what point? Displacement current is equal to conduction current. Already I have shown this. Both are equal to what? dq by dt. So therefore now, shall we give suitable explanation why there's a magnetic field? Because of this displacement current or because of that current density JD? Why the magnetic field is there? Because of current density. Once capacitor is fully charged, why there is no magnetic field? Because electric field is constant and electric field is not varying and there is no current density. So therefore there is no magnetic field. So why do this magnetic field exist? Because of varying electric field. Okay, this is the thing which I wanted. I'm not bothered after this RC circuit, what all that. So who is the source for this magnetic field? A varying electric field. So what is our conclusion? What is our conclusion? Therefore, now this conclusion is very important. Therefore, A varying electric field produces a magnetic field. So what is the source for magnetic field between the plates? A varying electric field between the plates. Fine. A varying electric field produces a magnetic field. So with